and in time t of n.
What's the time? There was no definition
Yeah.
of time.
That's a good point. The time is the number of steps that the machine makes before it accepts or rejects. That's why we need this very precise and basic model to be able to precisely define the time. The time is just the number of steps, the number of move heads. So this is for the single tape machine. For the multi-tape machine, it's well, actually it's the same. Yeah, because it's the number of steps that we make. Now, suppose that L is a language decided by a Turing machine with k tapes in time t of n. What it means is that when it has input of size n, then it makes at most t of n steps. It can make less than that, but not more. Then L is decided by a single tape Turing machine in time O of t of n squared. So the point is that if you have a multi-tape machine that decides a language, then you can build a single tape machine that decides exactly the same language, but maybe in longer time, but not too much longer. If this needs t of n steps, then this one will need t of n squared steps. T of n squared, not t of n squared. Okay. So how do we do this? What we need to do is to simulate this machine. Let's call it M. And let's call this one M1. Okay, so M1. We need to simulate M by M1. M has k tapes. We have to store its contents on the single tape of M1. So if you have, let's say, two tapes, tape 1, tape 2, and it's something like A, B, C here, and 0, 1 here. Then this is in M. Then in M1, we will have a single tape. And first we will have the contents of the first tape, so A, B, C. Then we will have a special delimiter symbol, like this one. And then we will have the contents of the second tape. So 0, 1. Is anything missing here?
Can I ask a question? M is after work or it's just language, yes?
No, M is a Turing machine. So we suppose that we have a Turing machine M.
Yes,
With k tapes.
why it's the second doesn't end?
Sorry?
The second type doesn't end, so it's after work, yes?
Yeah, it's after some work. Yeah, why isn't it empty?
Mhm.
Yes, because it's after some steps. Initially, it's indeed empty, but suppose at some point it looks like this.
Okay.
Then the tape of M1 should look like this. But there's some information that we're still missing when translating from here to here. What's that? Well, the position of the heads. Because here we have two heads. One may be pointing here, the other one may be pointing here. And we need to somehow remember it here. To do this, we introduce special symbols. So for each symbol of our tape alphabet, we introduce a copy with maybe a dot or something like that. And this, for example, B dot, would mean that if we see B dot in some cell, it means that the head of the Turing machine points to this cell. So we encode this information where the head points by the symbol that we store in the in our thing. So for example, this will be translated like this: B and 0. Is it clear? Okay. Good. So now we have to see how this works. So how the machine M1 simulates M. First, as you rightly said, we start with the input symbol, input word written on the first tape, and let it be ABC. And the second tape is empty. So this is going to be translated like into this. It's going to be A, B. Yeah, and the head points here and here. So here we will have A dotted. So here we have B, C. Here we have the delimiter. And then, well, one option is to have this blank symbol and, or maybe we can just, let's keep it blank. Blank symbol, but we put dot here. So dotted blank. Okay. Then when we make one step here in this machine, what happens here? First, to make a step here, we need to understand the contents of every tape. So we need to see where the head points here, where the head points here, and in any other tape, if there are any. So the first thing we do here, we go through this once, and we collect the information of the dotted symbols. When we understand what symbols are dotted here, we can check the rule that must be applied on this side. So, for example, we know that we're in state Q0, and then if we have a rule like A. Sorry, that's not how I write the rules. The rule could look something like delta of Q0, A empty, gets translated to Q1, B, C, R, for example. Right? So we first scan this tape to understand that which symbols are marked. Then we consult the table of the transition table of this machine, and we see that we must apply this rule, and then we apply it. How do we apply it? Again, we are here. We replace this A by B. I will write it here. Replace it by B. Then we have to move right, which means that here we have B dotted. Then this remains C. And then here we must replace this space, the blank symbol, by C. So here we have to write C, and we have to move here. And we move here just by putting a dot here. Okay, is it clear? So what may go wrong here is that if, for example, you have 3 tapes, then, so let's say if you have 3 tapes, with this, then if you have 3 tapes, it may happen that you have the delimiter here, then you have the delimiter here, and for example, you had a symbol here, but then the machine instructed you to move rightwards. So essentially you had to move here, which means that what you need to do, you need to move this portion of the tape rightwards, because it's like, you know, all these tapes of the multi-tape machine, they're infinite, but here we represent them by finite segments. So at some point we may need to enlarge these segments, and when we need to do this, we essentially move the contents one cell rightwards, so we have another cell, and we put our head there. Okay? Right, so this is the simulation. Why does it run in this time? TFN squared. Can somebody explain?
Actually, it seems that it won't be.
No, it will. First,
Well,
how much time do we need to simulate a single step on this machine? It depends on what?
Depends on, okay, on the number of steps and number of lengths. Okay.
Right. So, so actually, what's the time that we spend on the simulation? First, we need to scan the tape once, just to see what symbols are marked. Right? How long does it take? It takes as long as there are cells that are filled in here. But because our machine runs in time T of n, it cannot fill in more than T of n cells on each tape. So the maximum number of cells that are filled in here is the number of cells, the number of tapes multiplied by T of n. Well, roughly, because we also have this symbol, but something like this. Okay? But k is a constant. K does not depend on the input. It's just a characteristic of our machine. So essentially, this is O of T of n. This is the time we need to make one scan. Then we make a second scan to actually carry out the rule.
It also takes T of n.
Yeah, it takes T of n if we don't have to move anything rightwards. But at some point it may happen that we have to move stuff, right? Because like this, for example, here, the tape is finished, the segment of the tape is filled in, so we need to take this to empty one cell here, we need to move this to the right. But how many such moves may we need in one simulation, in the simulation of one step? At most k, because we may have to make it, or in the worst case we may have to make it for every tape. So it takes again k multiplied by T of n, but k is again a constant, so it's fine. So essentially we carry out this rule in time k of T of n, k times T of n plus T of n. And this is all of T of n again. So we simulate one step in time T of n. And there are T of n steps. So we have T of n squared. Is it clear?
Yes.
So, when we finish, by the way, at 20 minutes, right?
Yes.
So we have 8 minutes. Yeah, I wanted to show you something just a bit less abstract. I wanted to show you some Python code that can come out. So Turing machine, but maybe I won't do this because we have only 8 minutes left. What I should say though is that it is possible to I mean, if you take Python, it's not difficult to write a program that takes a description of a Turing machine and simulates its behavior, right? So what's the description of a Turing machine? Essentially, you have to describe this function, this transition function. And the transition function can be described as a table, so it's something that you can easily store in a dictionary, in a Python dictionary, for example. And then you can write a program that makes a single step by consulting that table. That's why we say that Python is a Turing complete language. You can simulate a Turing machine in it. But an interesting thing is that a Turing machine can be simulated by another Turing machine as well. So the first thing I should say is that it's possible to so for example, let's say we work in binary alphabet. So we work in an alphabet that has zeros and ones only. How can you represent a Turing machine in binary? So one possibility is to do it like this. So what's a Turing machine once again? You have Q, you have sigma, you have gamma, you have Q0, no, you have delta, Q0, Q accept, and Q reject. So you can encode this machine as follows. First, in binary, first n zeros, where n is the size of Q, the number of states. Then you put 1. Then you have m zeros, where m is the size of gamma. Then you have 1. Then you have k zeros, where k is the size of sigma. And the idea is that the first k symbols are from the input alphabet. So basically what you do here, you declare that you have m symbols in the tape alphabet and the first k of them are from the input alphabet. It doesn't really matter what these symbols are. You just integrate with them and that's sufficient. Then you have 1 and s, where s is s zeros, where s is the number of the initial state. Then you have 1 and r zeros, where r is the number of the accept state. So you say I have n states, and the state number s is the initial state, the state number r is the accept state, and then you have 1 and u zeros, and then we say that u is the number of the reject state. After that you have 1, and then you have the rules, the transition rules written down as follows. So if you have a rule like pi, so you are in state p, you see symbol I, so you have a rule like that. And then you move to Q, J, L. This is something that you can encode like this. First P zeros, then 1, then I zeros, then 1, then Q zeros, then 1, then J zeros, then 1, and then 0, meaning that you move to the left. And if you want to move to the right, you will write 2 zeros. So something like that. And you have this code for each of the rules from the transition function. So the point behind this is that you can represent a Turing machine as a binary string. And then you can have another Turing machine that takes a description of this Turing machine and a word, an input word, and it simulates that machine on that word. And this machine is called the universal machine. So, universal Turing machine. U. It takes as input M, some Turing machine M, but encoded, and an input string W, and it accepts if and only if M accepts W. So this is called the universal Turing machine. If you forget about, if you don't require this to be a Turing machine, but allow it to be, for example, a Python program, then what it says is that you have a program that takes a description of the Turing machine and an input word and just runs this machine on this word. And says yes if and only if the machine accepts this word. But the good thing about Turing machines is that you can do it with Turing machine. You don't have to, like you can't have the same for finite automata. You can't have an automaton that recognizes that decides whether another automaton accepts a string. That's not possible. But for Turing machines, you can do that. And we will meet these universal Turing machines quite a lot, in particular in the next lecture. Right. We're out of time, but there are 3 things I have to say still, because we will have exercises about them. And these are complexity classes. So I'll do it quite quickly. We will need at least 3 complexity classes today. One is called P, and that's the class of languages decidable in polynomial time. So maybe I should, I will use this notation as well. Time of f of n, that's the set of languages decidable in time O of f of n. So P is the class of languages decidable in polynomial time. You can define it as follows. It's time, the union of time of n to k for all constants k. So everything that can be decided in O of n squared, O of n to 100 goes here. That's polynomial time. Of then, there is also a class called exp time. And it's essentially the same stuff, but instead of n to the k, we have 2 to the n to the k. So these are problems or languages decidable in exponential time. But besides time, we will be, I hope it's clear that P is a subset of exp time, right? If you can decide something in polynomial time, then of course you can decide it in exponential time. What's not obvious is that they're different. So there is indeed a problem. There are indeed languages that are decidable in exponential time, but not decidable in polynomial time. And that's the topic of the next lecture, or rather consequence of the topic of the next lecture. So this inclusion is proper. talking about space. And we can.
No, we cannot. Excuse me.
Yeah.
May I just
Okay.
thank you?
But you should consult Sipser. It's written there better than in better handwriting than mine. So besides the time, we will be also talking about space. And space is defined like, well, analogously. So space of f of n is the set of languages decidable in space O of f of n. What it means decidable in space is that, well, what's the space that a machine needs? It's just the number of cells that it scans through its operation. It may go to the same cell twice, but this is counted only once. So basically that's the portion of the tape that the machine uses. This is space. And then we have a class p space, which is also an important complexity class. Which is defined exactly like p, but for space instead of time. So, what do you think? What's the relation between these three classes? P and p space, which is bigger?
Space?
Yeah, p space is bigger, or potentially bigger at least. So we have that p is a subset of p space. And this is because you can't use more than a polynomial polynomial number of cells in polynomial time. Because a Turing machine at each step may use one more cell at most. Either it goes back to a cell that it saw before, or it goes to a new cell. Because it makes a polynomial, if it makes a polynomial number of steps, then it can't use more than polynomial number of cells. And what about p space and x time?
X time, I think, potentially bigger than space.
Yeah, that's true. So indeed. And I think I have to explain it at least briefly, because there will be some exercises related to that. So why p space is a subset of x time? Well, if you have, so suppose you use f of n space. Then how many configurations of the Turing machine can you have? And that's a definition that I forgot to say. Configuration of the Turing machine. Configuration. It consists of three things. First, it's the state. Second, it's the head position, which cell it points to. And the third is the contents of the tape. That's what's called a configuration. Now, if a machine never loops forever, if it can't enter an infinite loop, then it's not possible for it to enter the same configuration twice. So if it was in some configuration and then it's again in this configuration, then it will be again in this configuration, there will be a loop. So during its computation, all configurations must be different. And now let's count the number of configurations when the machine uses only f of n space. Well, a configuration is so the number of states. It can be in any one of this many states. But then its head position. must be on any cell, and because we use f of n space, then it may be in one of f of n positions. And then the contents of the tape. So what are the contents of the tape? On the tape, in each cell of the tape, we may have gamma, each of these symbols, each of gamma symbols. And because we have f of n cells, we have gamma to f of n. So this is the maximum number of configurations. But q, this is a constant, so we can ignore it. And the gamma is also a constant. So this is O of 2 to something like, or maybe it's better to write it differently. It's 2 O of n. O of, sorry, f of n. And because f of n is a polynomial, this is going to be this, 2 to n to the k. And that's why p space is a subset of x time. So you can't have more. The total number of configurations is this, and no configuration can repeat. So you can make it more, the machine can make it more as many steps before it stops. Okay, so what we know? We know that P is a subset of P space, we know that P space is a subset of X time, but we don't know about these inclusions. Maybe they're proper, maybe they're not. All we know that at least one of them must be proper, because P is not equal to X time. Okay. You have any questions?